and study this workshop. I'm sorry to anyone who came expecting to hear David speak. I'm going to be talking instead. The reason is David Ray gave a very nice introduction to how recently people have used massive gravity in the holographic literature to model systems that don't have a conserved momentum and study their transport. And in the last couple of weeks, we've done some very recent work on this, and basically, we want to tell you about this. So the point of my talk is to explain something that should be quite natural, which is how, if you break translational invariance using some, say, a lattice in holography, how that's related to giving a mass to the graviton. So basically, everything I'm going to say will actually be quite simple, but it will hopefully make everything make a lot more sense, is the idea. Okay. Do these move, or do I? Okay, so I'm going to tell you about holographic lattices and how that's related to massive gravity. Okay. So this is going to be based on some work that I've been doing with the two Davids, David Tong and David Bay, who are in the audience, in the last, well, certainly in the last month, and especially in the last week and a half. So this is very, very recent work.
I did it twice, Mike.
Oh, yes, you did. We'll have to make sure that's not like that on the paper. And so this is very recent, so if anything's like slightly vague or not perfectly clear, that will be why. But hopefully there's a nice physical story, so the physics should hopefully be very clear. And we're going to use some work that David Tong and I did last month. Okay, so this one's on the archive, and since I only have like 3 papers, it should be easy to find if you just look at my name. Okay, so the first thing I want to do is to I'm going to have a little introduction, and we've had a lot of talks about studying conductivities and breaking translation invariance in holography. But what I want to do here is to make sure we're starting from the same point, and so set our expectations basically about what we could possibly hope to achieve in a relationship between a holographic lattice and massive gravity, just basically by telling you stuff you already know. That will just clarify what's going to happen. And to be honest, at this point, you'll know exactly what's going to happen in the rest of the talk. It basically gives the game away. And then I'm going to just go on to actually explicitly tell you what to do, explicitly tell you how it works in a toy model. So I'm going to take the simplest holographic lattice that I can study. So normally it's very hard to study these things because when you put a lattice into Einstein equations, it's non-linear and everything gets very messy. But we're going to just pick a really simple case where we can get around that problem and tell you that basically the only effect of this lattice is to give a mass to the graviton. That's basically all it does. So massive gravity. And then I'm going to use this relationship between these two ideas to calculate the DC conductivity in these theories analytically. So this is the bit that's based on what David and I did last month, where we showed that in theories of massive gravity you can get an analytic formula for the DC conductivity very easily, and we're going to apply this using this relationship. We can apply it now to a lattice, and we're going to arrive at a formula for the DC conductivity that actually agrees with something that's been known in the literature, a result derived by Sean Hartnell and Diego Hoffman, who derived this formula from a field theory point of view, but we're going to now derive it purely from a bulk gravity point of view. That's basically where we're going.
That's always going to be an irrelevant lattice.
Irrelevant lattice, yes, in the IR. Exactly. Basically, because it's got to be an irrelevant. Basically, the philosophy is we're going to have to try and treat the lattice perturbatively. Otherwise, we've just not really got any hope. So it's going to have to be a small lattice, especially in the IR. And that's the philosophy that Hartnell and Hoffman used in their approach as well. So we're basically going to mimic that, just in the bulk. That's the idea. Okay, so I'll start just at the beginning, which is that perhaps the main motivating question behind all this work on ADS-CFT and condensed matter, or at least one of the main things, is to try and answer the question of how we talk about the transport properties of materials, or just transport in general, when we can't rely on the Boltzmann equation. So what we'd really like to get are some organising principles, just some nice framework by which we can understand how these systems behave. So this is really our question. So what are the organising principles for transport? And this is a lofty and noble question, but in practice we don't really attack this directly. We just use the fact that we have ADS-CFT and we can just calculate things, and then hopefully from those calculations we might be able to extract what the lessons are. So in practice we just calculate things, and the most physical thing we calculate is just this conductivity. So how well these holographic theories conduct electricity. And what we learn is that holography does a pretty good job at getting these calculations qualitatively right. So at high frequencies, you find that the conductivities, so this is going to be I'm always going to be in 2+1 boundary dimensions and 4 bulk dimensions. So you find that the conductivity is just some constant at high energies because we're in a CFT in the UV. It dips down at some scale set by the chemical potential. And then if you don't break translational invariance, this is really all that happens. It doesn't really do much over here. There might be some power law there, but that's not that important for this talk. But what is important is that you have an infinite conductivity here at 0 frequency. So you have a big delta function sitting here, and that follows just on general grounds that when you have some charge and you apply an electric field, if it can't dissipate any momentum, it just starts accelerating. So in the last couple of years, there's been a lot of work in the literature asking what happens if you violate momentum conservation and you sort of smooth out this delta function due to some scattering processes, and rather than being infinite, the DC conductivity is now finite, and you get some Drude peak. Okay, and this is nice because there are now some interesting questions you can ask. So one question you can ask is, what's the height of this peak here at 0 frequency? So you can ask, how does this DC conductivity, the value here, depend on temperature? Perhaps there's some nice power law relationship that you can study. And the second question you could ask is, perhaps something interesting happens here in this tail of the Drude peak, and maybe as a function of frequency there's also some power law that you observe here. Okay, so these are two different questions you can ask, and perhaps they're unrelated, or at least the way you might want to tackle them in holography is. So this question here is really hard to get at using holography, and really the only work that's made progress on getting something interesting here is David's work with George Santos and Gary Horowitz, where you treat the lattice numerically using partial differential equations, and then you can kind of try and get in at this region and see something happen. And I'm not going to say anything about this region. It's just basically too hard for us at the moment to understand, but maybe one day we'll get there. So I'm going to focus here on this DC conductivity, which is a bit easier. And as Blaise said, the reason is there's this idea that if you have an irrelevant lattice in the IR, it's going to be a small lattice until you can make progress perturbatively. You might hope that if you just break translational invariance a little bit, you can work in perturbation theory with this lattice and try and understand this value here. So that's been done on the field theory side, and I guess it's it is an organising principle for transport at least, and it goes by the name of the memory matrix. So there's this thing called the memory matrix formalism, which is an old condensed matter approach dating back to, I think, the 50s or 60s. And last year, Sean Hartnell and Jacob Hoffman used it to ask, can you get power law resistivities in strongly interacting field theories? And the answer is quite interesting. It's generically extremely hard to get a power law DC conductivity from a field theory. And the reason is that you need some low energy excitations that live at finite wave vector. And so, for instance, in a relativistic theory, that just can't happen. It's going to cost you some energy to have an excitation at a finite wave vector. And so generically, you might think this won't happen in holography. Of course, condensed matter systems get around this because they have a Fermi surface, so things can move around on the surface of the Fermi surface, exchange some net momentum and still not change their energy, and that's what gives a power law resistivity in real material, in, well, Fermi liquid materials. And then it turns out there's one third option, which is when you have a local critical scaling. So local critical scaling is when time scales and space doesn't, and it means that actually momentum doesn't cost you any energy. So in that situation, they derived a formula for the DC conductivity, which is better to write in terms of the resistivity, the inverse. If you deform your theory by a lattice, you turn on a small lattice, so you turn on some operator that breaks translational invariance. It's at some wave vector k, and you just turn it on a small amount. You find that you can derive a formula for this in locally critical theories, where the conductivity scales as this small parameter squared. There's some factors of the wave vector, and then you do get a power law resistivity. But interestingly, you get a very weird exponent for this power law. So this power law depends on the dimension of this operator O under this locally critical scaling. So from a holographic point of view, it's the IR scaling dimension of this operator. That's important. So this is what you learn from field theory, and I've allowed the scaling dimension to depend on k, and that's because in these locally critical geometries it does, because momentum is just a label rather than being just like because of the scaling, basically. So the goal of this talk is basically to show you that this formula, which comes from the memory matrix, so it's perhaps a slightly old-fashioned way of doing things that maybe we're not that familiar with, can be understood simply just from a bulk point of view using holography. And the key idea is that we're going to be able to relate the DC conductivity to the mass of the graviton that we're going to have in our theory.
You said this numeric formula is only valid for these, what did you call it, critical local scaling theories?
So the memory matrix formula is always valid, but this particular formula I've written down, so there's a more general formula that applies in general, from which you can deduce different things, where you can deduce how it would behave in different circumstances. This particular formula I've written down here, by which I mean this power, is specifically for the locally critical geometries. But you can apply it to, say, a Fermi liquid and get that the resistivity of a Fermi liquid scales as T squared. It's just not related. It's obviously not this IR scaling dimension in local criticality in the same way.
But is it only for ADS equals R2 or is it also for conformal case?
The memory matrix formula. In this talk, I'm going to do ADS2 plus R2.
Yeah.
But I'm not 100% sure what the
Hoffman, they do it for ADS2 plus R2.
Sorry? Okay.
Hoffman do it for
Right.
ADS2 plus R2.
The memory matrix formula always works. The question is, so there's a more general formula than this, which is just always true, and you can then do a renormalization group argument scaling to understand what the power is. Their renormalization, their general formula will always be true. I'm not 100% sure in another theory whether this is the same power or if it's shifted by a small amount depending on, say...
It probably wouldn't be the same power, but the question is, could you also derive
you could also,
scaling law?
yes, you could also derive the same scale. You would also get a power law resistivity which would look like this with maybe some some number out the front. That was your conformal scaling.
Yeah.
Yeah. You can.
No,
You don't have locally critical theory, so you don't have an ADS2 region in the infrared. Then you don't get a power law at all, right?
If you're conformal to ADS2, you still do.
Well, see, that was the question.
Yeah,
There's
yes.
no
If you're conformal to ADS2, the same thing happens, but rather than being 2 to the scaling to this delta, it might be 2 to the delta plus some extra thing that's related to the conformal factor.
because we still have this scaling argument, right?
Yes, exactly. So the same. Yeah, exactly. It's just the scaling you need to have a power law. Yeah, that's right. Good. But I'm going to do it in ADS2 because it's just a little bit cleaner for today. Okay, so I want to start by just setting our expectations. So this will make it very clear, actually, what's going to happen and how I'm going to proceed. Actually, I guess I can just push this up. Come on. Okay, so expectations. Okay. So the thing I want to just remind you of here is an analogy between what we're trying to do and a more familiar case. So what we want to do in all of this is to break the momentum conservation in our boundary field theory. So we want to have a stress tensor in the boundary that doesn't have a conserved momentum. Okay, that's our idea. And this is just the same as having U1 current, having some current that's not conserved in the boundary theory. So if we wanted to study holographic theories where this was not conserved, then there are kind of two qualitatively different approaches you might try. So the first thing you might do is to have a massive vector field in the bulk. Okay? So you're just going to add to you're just going to have a massive vector field, you're just going to have some constant mass term in your action. Okay? And morally, this was the motivation behind studying massive gravity. If you want to break this conservation law, you just study a massive vector field. And if you want to break momentum conservation, well, just study a massive graviton. That's going to be the right thing to do. But there's also a second option, and that's to break the gauge symmetry in the bulk using some charged operator. So effectively have like a charge scalar field, turn it on, and it's going to break the gauge symmetry and violate the conservation law. So, either explicitly or spontaneously break it. Break a U1 symmetry using a charged operator. Okay, so this is just basically the Higgs mechanism. You Higgs your gauge field. Okay? So this case is effectively what you're doing when you're studying a holographic lattice. You've turned on some operator in the boundary theory that breaks the diffeomorphism symmetry in the bulk. So are these two the same thing? Well, no, they're not the same thing. In general, you're going to get quite different answers. So for instance, if you wanted to ask what do the background solutions to these two theories look like if you solve them holographically, they'll be completely different. Because in this case, there's just an extra mass term in the Lagrangian, whereas here there's a whole scalar field that has its own kinetics, and that's going to affect the stress tensor and completely change what the geometry might look like. But on the level of the perturbation equations, these can be very similar. So of course, this will give some effective mass to the gauge field, but it's some effective mass. So there'll be some effective mass term in the action. So if phi is my charged operator, that's breaking my symmetry because I've turned it on. It's going to Higgs the gauge field and give it some mass. And if you look at the perturbation equations, if you've ever done this calculation, and look at what happens if you try and calculate the conductivity in this case, and compare it to that case, say, you'll find that the only way the presence of this charged condensate enters is through this effective mass term. So on the level of the perturbation equations, if these two are almost exactly the same, provided we generalize the mass to just now some function of position, that depends, of course, on the operator that's actually broken my symmetry. Okay? So this is all very natural and very simple, and the entire point of this talk is to tell you that the same story happens if you're studying, if you're talking about massive gravity.
So if the symmetry is spontaneously broken, then the current is still conserved, right?
So explicitly break it by turning on the operator in the...
So unless you turn on the source.
I'm thinking of turning it on as a source, yes.
Right, so it's only explicitly...
Okay. Explicit. Yes. Yeah, okay, do that. Yes.
So it's third option too if you have anomalies.
Sorry?
Anomalies is option number 3.
Options number 3. See, that would be interesting.
Anomalies.
Yeah, I've not thought about that, but that would be interesting. But you see this, you all understand how this works. And all I'm going to tell you today is that it's no more complicated, at least in the story I'm going to tell you. So you know where I'm going to go. Okay. So I say it's no more complicated, but that's not quite true. And the reason it's not complicated is the lattice does lots of things. So if you have a lattice, it breaks diffeomorphism invariance in the bulk, but it also starts making my geometry ripple when it back reacts on my geometry. And I don't really want those effects because they're going to be there and they're important and it would be nice to study them, but they're sort of qualitatively different to this effect. So it would be nice if I had some toy model where I can kind of separate these two different effects from one another, and for now, as a first step, just study this effect of Higgsing in the bulk. And that's what we're going to do. Yeah. Okay, so the way you can do that, okay, so the way to separate these effects is to effectively work perturbatively in the lattice strength. So if you turn on a lattice in general, it's very complicated, as I said, because of the fact that you source an infinite number of modes due to the nonlinearities of the Einstein equations. So what you have to do to really make progress is to truncate at some order in perturbation theory in the strength of this lattice operator you've turned on, and at any order there's going to be some finite set of modes that you might hope to study. So I'm going to do this in literally the simplest way I can. So I'm going to turn on a lattice that sources the least number of modes, which is, at least I think, the natural place to start, the simplest possible case. So I'm going to have a background, and I said earlier that in order to get a power law resistivity, I'm going to need a locally critical geometry in my IR. So it's just going to be a Riemann-Norton black hole. That's going to be the initial background geometry. So I'll just have the standard action, Einstein-Hilbert, or a Maxwell term, and I'll turn on a charge density for this theory, so there's some electric field, and that will support a locally critical geometry, which is going to be the Riemann-Norton black hole. And to zeroth order in this lattice strength, this is the entire story, you know what to do. So the next thing I do is I just add some small lattice using some scalar field. So this scalar field just doesn't really matter what mass this scalar field has, apart from which I'll clarify in a second. And of course, I'm just going to turn this guy on so that it's got some lattice rippled structure, and so it breaks the diffeomorphism symmetry. So psi is, I'm just going to write it as it's just going to turn on with some radial profile, which I'm going to call this psi 0, and then there's just going to be a cosine at some wave vector in the x direction. I'll just turn it on in the x direction for now, because it's just simpler. And I'm only going to turn this on a small amount, epsilon. So it's going to be a tiny lattice everywhere in my bulk, and I want to study how that affects my transport properties. Now you might worry that I can't do this consistently because, for instance, this field psi 0 of r might blow up somewhere, say near my UV, and so I can't consistently treat my lattice perturbatively. But what you actually find in these geometries is that these lattices have a typical profile where they actually, so this is going to be my geometry, and I'm going to plot this psi 0 of r. And roughly speaking, what happens is you can choose this mass so that they don't blow up in the UV, they're small here, and then they get bigger and bigger, but they approach some maximum value, and then they start getting smaller and smaller again in the IR. Okay? So if this is my radial direction, and this is 0, which is the boundary, the UV, and there's a horizon of my black hole at RH, the lattice profile will just be sort of bounded like this. So I'm going to be able to treat this consistently within perturbation theory. I don't have to worry about it blowing up anywhere. Okay, so yeah, that's really the key point here, that we can do this consistently. Okay?
What do you do with this?
You'll see that's the next point. Okay, so the next point is, why did I choose this particular scalar field? Why did I do it with a scalar and not turn on a gauge field, a lattice in my gauge field and my metric? And the reason is that I actually want to isolate just this one effect. So the point is that if I turn on a lattice in my scalar, the stress tensor is order epsilon squared. And that means that the oscillations in the lattice and in the metric, caused by the fact that I've turned this guy on, are higher order than the oscillation in the scalar field. And so I can consistently neglect them at leading order. And so in this model, which admittedly is just it's a simplification, but this is a consistent simplification. And the only oscillations I'm going to have are in my scalar, and everything else to this order is just homogeneous. And you see that's the key assumption that allows me to make progress here very easily. There's hardly any extra degrees of freedom turned on. So that's why I've done it in the scalar.
Is there any thing that matters when you try to insert this in the boundary theory? And so when you do it by boundary conditions, it's really like as if you have ionic potential for dielectric charge, and what would this be?
Yeah, I guess I've not caught. This is supposed to be something in the. I want to have sourced this.
Yeah.
I want this to be explicitly sourced. This function to be explicitly sourced in the boundary theory. Yeah, that's what I want. But off the top of my head, I'm not sure where that essentially comes into the argument, but that's what I'm thinking of doing. Definitely. Yeah, it should be an explicit lattice sourced in the boundary theory. So, I mean, I don't want to write down the profile because it's going to depend on the mass, right? What the scaling is in the UV. But yes, this should be an explicit source.
So here, the phi is relevant.
It's relevant. Let's get this right.
And
It's relevant in the UV.
I mean, if phi was uniform, it would keep growing.
Yeah, yeah, good. So the reason it gets pulled down is because of this.
And does the peak position scales inversely with Kf?
I guess it has to, doesn't it?
Right. But is it just power is -1 or?
I don't know. I'm sorry. Off the top of my head, this is just schematic because this is just supposed to be schematic. I don't know the details. It won't matter at all in this talk. What we're going to learn is that all that matters is what's going on in the IR.
And is that the power at large R?
At large R, it's a power law. Yes, that's going to be crucial. Yeah.
Just to understand, so you solved the field equation for phi in the Rice-Nelson black hole, and you found the profile phi not of phi.
Yeah.
Yeah, and has that shape.
It has that shape. Yeah, exactly. This is schematic. This is the solution. It's of this form. So it's sort of justifying that treating it perturbatively is consistent. Yeah. Good.
Is this an analytic solution? Is it a numerical? Is this possible?
Everything I'm going to say does not depend on the form of the solution. So you'd have to solve it. I think numerically you'd probably have to solve it. But so this is a key point actually. Everything I'm going to tell you today is independent of the form of this guy, except for his behavior in the IR, which I'll be able to look at analytically. It's independent of. I actually have to take into account the homogeneous part of the back reaction on the metric and the gauge field, completely independent of what that does. And the reason is I'm going to end up using a sort of universality argument later on. So we'll get to that point. Basically, it just doesn't depend on the details of this geometry. You'll get the same answer whatever happens.
So to what extent is the algebraic nature in the deep infrared important? What would happen when you would have sort of an exponential fall off in mass scale there?
In the IR, you mean?
Yeah.
That's important. That's related to the fact that in order to get a power law resistivity, we need it to be in AGS2. It's the same point. It's the same point. Yeah, exactly the same point. I mean, yeah. We'll get there later. We'll get there. Good. Any more questions? Okay. So this is the idea. We're just going to treat this perturbatively. We're going to have a lattice in the scalar field, and everything else is homogeneous. And that means that we're only going to source like a couple more degrees of freedom than we otherwise would have done in the standard calculation. Good. So this is our background solution, and I told you schematically what it looks like. And as I said, we don't need its exact form. And then what I'm going to do is to perturb this solution to try and calculate the conductivity and look at what those fluctuations kind of will do. So if you want to calculate the conductivity, the thing you have to perturb is a change in the gauge field AX to correspond to an electric field on the boundary. And the mode you source is just a function of R and T. This will back react on the metric, because there's some overlap between momentum and current in the boundary. And in the normal Rice-Nelson black hole, this is the end of the story. You have these two you have these two fluctuations, you can fix the gauge such that nothing else is sourced by setting this guy delta G Rx to 0, and then you can eliminate delta GTX, and it's the first thing you do in holography if you're working in this field, is you learn how to solve that equation and calculate the conductivity. So what I want to ask is what happens now that we've just turned on this very small lattice? How does the story change? And there are two effects. So the first effect, which you could probably guess coming from this action, is that there's some coupling between the metric and the scalar field that's going to source some scalar field perturbation. So there's a scalar perturbation. Okay? And you find that rather than being at okay, so so there's a scalar perturbation, and because these perturbations are odd under parity, it's not going to be related to cos, it's related to sine. So you get something that's proportional to sine kx. And you want to, and then there's some function of r and t out the front describing this perturbation, and it's very convenient to actually take out this overall amplitude of the background field as a factor, and you'll see why in 10 seconds. So you take out some overall factors of radial position, and then we'll call what's left here pi of r and t. That will be the relevant new mode introduced by our lattice fluctuation. So the reason you strip out this factor is that you see that this fluctuation is proportional to a sine, and the background was proportional to a cosine. So if you use the double angle formula, you can package this all together. And what you're left with is that this extra mode is nothing but a change in the phase of the lattice. Okay, so this is the extra mode that we source in this calculation, and all this is that the phase of our lattice can vary now as a function of radial position. So it's
in a way it's a bit confusing, right? Because the lattice is explicitly broken.
yeah,
So in space directions there's nothing of this thing. And now you find that there's still a freedom along the radial direction. Here it really comes, right?
yeah. Well, I mean, it only costs you gradient energy is the point. I mean,
Yeah, right. So when you have this really fixed lattice on gradient, then it use R infinite, right? Basically like
well, I
that.
mean, the lattice is fixed in the UV.
Yeah.
It's not fixed
Thing.
everywhere. It's only at the UV that it's pinned
Yeah.
to be at a certain point. So in the bulk, it can move away from that as a function of radial position. So, I mean, what's going on here is you've got this, so at every layer in the bulk, you have a lattice with some ions in it.
These are your phonons.
Yes, precisely.
Yeah, but the phonons are
That was my next point. This is a phonon. This is precisely a phonon.
But I thought that this was a setup where you really freeze the lattice. It's like an optical lattice. An optical lattice has some phonon.
It's a radial phonon, though. It's not a phonon in the...
Exactly.
Yeah.
So in space directions,
Yeah.
all frozen.
Yes.
Tilted. I'm just trying
Oh, yes,
to
yeah.
understand where it is, right? And then remarkably, because the radial direction is a scaling direction, you still have
Yeah.
it's somehow related more to the renormalization flow than to
Yes, it's somehow a renormalization flow
Yeah.
thing, yeah.
So you have automatically freedom left that you don't pin, right? You only pin it in space direction.
Yes. So you see, if this is my radial direction, there's this, at each point in space there's these ions in my lattice, and they're pinned in the UV to have certain values, which are the values of the lattice in my boundary theory. But as I move away from that position, these can start moving relative to one another, and that's just this excitation. And then this excitation can propagate in the radial direction, like this. And so this is what you'd call a transverse phonon, because the oscillations are perpendicular to the direction of motion. So it's a transverse phonon that can move in the radial direction. So this is an extra mode you excite.
Right, so it's on every space slice, you have the same lattice,
Yes.
and then along the radial direction, you have that freedom.
Yeah.
So I think it's a normal phonon. Very interesting.
Yeah.
Renormalization type of thing.
Yeah. So this is one thing that happens. It's not the only thing that happens. There's a second effect. which is important, and it's actually going to be hard for me to explain very clearly because this probably won't convince you, so you're going to have to slightly take this on faith. But this also gives the graviton a mass. So for a second you're going to have to believe me. And the way to see that this gives the graviton a mass might not be that helpful if you've not worked with massive gravity before, but if you have, it's kind of helpful. So the way massive gravity breaks diffeomorphism invariance is that it adds an extra term to the action, okay? And that extra term is a bit weird, and it looks roughly, morally like this. So it looks like you've just added, this is supposed to be the constant graviton mass. It's like you just add a gxx upstairs to your action and start integrating that over space. So this clearly breaks diffeomorphism invariance and is like not the nicest thing in the world to do. But that's what it looks like, and the reason this gives a mass to the graviton is that when you expand this determinant as like 1 plus delta G, something like this, you know, when you take into account fluctuations of the graviton, this has some quadratic piece, and they acquire a mass from this term. So you can see from our kinetic term in our scalar field action that there will be a similar term to this that has a gxx in it, coming from the so if you have a lattice, there's a term that's very similar coming from the x derivatives, the kinetic term of the lattice. So there's a term that looks like gxx dx phi squared, okay, in the background solution. And so if you write down what this is on a solution of our form, it's square root of gxx, and then you pull down, you have to plug in the background solution in here, you get epsilon squared kl squared psi 0 of r squared. Okay? So actually what you see, and this does work if you do this properly, is that the graviton from the expansion of this acquires a mass, and that mass is related to the scalar field. So there's an effective mass, m squared of r, that looks like epsilon squared kl squared psi 0 of r squared. So this is the effective graviton mass. Okay, and yeah.
Wouldn't there also be a sine squared of x?
Yes, sorry, I've taken the homogeneous part of that. So sine squared is 1 plus cos 2. And this is the 1. Yeah, good. That's right, yeah.
Right, so the deep wisdom is, we start out with Einstein's theory, right? It's all diffeomorphic.
Yeah.
And then there's a right-hand side of the equation, and there matter is sitting, and matter decides to break global translation in the first place, but where your global translation automatically sacrifices the diffeomorphism,
Yeah.
you expand it out,
Yes.
and then
Yeah.
you see that.
And I think this is just seeing that explicitly, I think, yes. So this is just the analog that we saw, of this Higgsing earlier. You get some effective mass for your graviton, and rather than being a constant beta just sitting in your action, it's got some dependence on, of course, the lattice, which is the operator that's broken the symmetry. So this is what I meant by the analog of the Higgsing. So these two things look like completely different phenomena at the moment, the existence of a graviton mass and the fact that we have this extra mode. In fact, they're kind of exactly the same thing. And the reason they're exactly the same thing is because this mode is only physical because I picked the gauge grx is 0. So that was a gauge fixing. I could switch to a different gauge. I'll just write this here. If I switch gauge, so switching a gauge is just changing my coordinates. If I define a new coordinate, x plus pi, okay, then this phonon excitation is not an excitation at all. By defining this new coordinate, I've completely fixed my lattice to be still in this new coordinate system, and it doesn't move at all. Of course, something else happens, which is that I have to change my metric by this coordinate transformation, and I now turn this grx field on. So this would imply that you get a non-zero delta grx. Okay, and this is the extra degree of freedom that a massive graviton would have. So this is precisely the Higgs mechanism. This guy here is basically a Goldstone mode, and when I've moved to this gauge, the Goldstone mode has been eaten by the graviton and is manifesting itself as its extra degree of freedom. So although this looks like two different things, once I've fixed my gauge, they're actually the same effect.
I'm a little confused. So you turn on periodic potential at boundary.
Yeah.
So therefore, this phono mode is not gapless. It's not actually transverse mode. It's longitudinal.
It's a transversal mode along the
Yeah,
radial
right.
direction.
Yeah, that's right.
Right, so the boundary can see it because it's a
Yeah, I
radial
understand,
direction.
but they are gap mode.
Okay.
That's not the issue, eh?
It still works like this. You can still pick a gauge where it goes away.
I mean, at each point in the bulk, it's locally gapless.
Yes, that's what I think. I think it's gapless, but just pinned by boundary
It's pinned
conditions.
here, but it can really.
Yeah, that's what I think. I think it's if you're in the IR, you can't possibly tell that in the UV you're being pinned to take some value, right? You don't know that there's a boundary condition in the UV forcing you to. So basically, pi bar is going to satisfy some differential equation, and the fact that it's pinned in the UV is just providing a boundary condition for pi bar.
I guess if you compute two-point function for that network,
Yes,
it will be gap.
presumably yes, but on the level of, this argument doesn't depend on whether it's gapped or not. You can still, you can see. This is the expectation you get, and I can still gauge it away by introducing a new coordinate.
You cannot gauge it away at boundary.
I can because it's not there. It's not turned on at the boundary.
It's fixed to be 0 at the boundary.
Yes, yeah, it's fixed to be 0 at the boundary. So it's exactly.
So I would be prejudiced, right? It's again simple Einstein theory, and it's something you don't meet easily in normal applications, but matter is a very important thing. There's no opinion. It can break translations. And at the moment you have a lattice, you have a real preferred frame. Right, when it back reacts on space and time, the space and time just lose the variableism. Right, and that's a bulk phenomenon.
Yeah.
Right, they can
Yeah.
perhaps also imprint that by the boundary condition. So it's very deep symmetry principle. So to get massive gravitons, you have to lose that to variableism. And this is it, and it seems very natural.
Yes.
This is often looked like this in
I
the grand history of GR, but
Yeah, I completely agree with all your points. I think they're all valid points. I agree. It's not immediately obvious that this is not spontaneously breaking the symmetry. You might think it's not massless, but locally it is.
no, but when you break spontaneously the symmetry, it has still the same effect.
Yes,
Right?
exactly.
When you have this table,
I see.
you have a fixed frame out there.
No, then it's different. Then phonon is really gapless. If it is broken spontaneously.
We're not talking now about the phonons of the crystal. We're talking about the way that this crystal is fixing the frame, thereby making the gravitons massive.
Yeah. Right, I think I should just get on with the story,
Yeah.
because this isn't an essential point.
You always have the black hole in the IR.
Yes.
So this sets a temperature, that's
Yeah.
a scale.
Yeah.
Do you see some change of behavior? Because you have two scales, the scale of the lattice and the scale of the temperature.
Yes.
So as you increase the temperature, that would, I think, might prevent or hinder this.
Definitely.
So you see that?
Well, not in what I'm going to tell you today, but it should be there, yes. I'm going to be working at those temperatures.
Okay, so it's always temperatures that are much lower
Yeah.
than, okay.
Okay, so let me tell you now, so hopefully I've convinced you that actually all we get in this model, which is what I wanted to convince you, is you just get basically massive gravity, but there's some effective graviton mass here, and you can interpret physically the way massive gravity dissipates momentum by working in a different gauge, and you see there's this transverse phonon. So now I want to tell you about how you can calculate the conductivity analytically in these theories and get a nice simple expression for it. Okay, so this is actually quite a simple argument, but it's also slightly surprising. So I'm going to have to write some differential equations on the board, which isn't ideal. So I'm going to do it in a very schematic form, and you can basically ignore all the details. So we have these perturbations, and in this gauge there's AX, GTX, and then there's phonon mode. And I can get rid of GTX using a constraint, and so I end up having to solve two equations that are coupled together to calculate the conductivity. So schematically, these have the form that there are there's now these two modes, the gauge field and the phonon. Okay, so these guys are just some radial derivatives that are going to act on these perturbations. These are the time derivatives that are going to act on the perturbations. And then there's some mass matrix M that couples these guys together. Okay? So if you were to do this in the Horizon-Norton black hole without this extra phonon mode, you just have the gauge field. So if we turn pi off for a second, you find that this fluctuation here of the gauge field actually is massive. So there's a mass for the gauge field, and it's a mass that's set by the chemical potential. So there's a term that looks like this in the equations of motion. And this mass is ultimately what was responsible for the fact that in translation invariant theories we had an infinite conductivity. If you work out what happens, this causes there to be this pole and then a delta function in the conductivity. So something quite nice happens when you turn pi on, and we don't still really understand why this happens, except for the fact that it kind of has to, which is when you turn pi on, this mass matrix is actually degenerate. So the determinant of this matrix is 0, and that means that there must be some mode, some combination of AX and pi that is massless, because there's some eigenvector with eigenvalue 0 of this matrix. So this tells you that there's some massless mode that emerges once you take into account the fact that there's a phonon. Yeah? Sorry, did I just hear my echo? Good. Okay, so some massless mode emerges, and that's okay. So the reason this emerges is because rather than just being diagonal, there's some off-diagonal terms coupling A and pi together, and that's what's responsible for the fact that you now get this massless mode. And there's a remarkable thing about AJCFT, which is that when you have massless modes, you can do something very nice, which is due to Nabil and Hung Nu, which is that you can basically, when you have massless modes, in the low frequency limit, they don't really evolve between the IR and the UV. And that means you can tie IR quantities, so you can tie UV quantities, such as the conductivity, the recipe for calculating the conductivities in terms of some UV data. You can tie that to properties of the IR or just of the horizon. So the way you do this is you define some conductivity, some analog of the conductivity at every point in space. It's some generalization of it. And then if you have a massless mode, you can argue that this DC conductivity is just a constant. And so it doesn't depend on where you are in space. And so you can just instead evaluate it at the horizon. Okay, so that's what you can do, and you can then just calculate this straight away. It's just some number, and you know what the DC conductivity is. So this is what David and I did in theories of massive gravity, and you find an interesting answer. You find you can get the answer completely analytically, and it's just very simple. There are some factors of the charge density, and there are some factors of the horizon radius, which are just required by dimensional analysis, and then you find that the graviton mass is the thing that controls the conductivity. And it's this graviton mass, obviously evaluated at the horizon, that's the relevant quantity you need to understand.
Is you cannot relate the numerator to viscosity or something?
Not obviously.
Not obvious.
Not obviously. So this just drops out of this kind of simple analysis straight away. You can trade the DC conductivity for the graviton mass. They're basically capturing the same information. That's the idea. And there's a nice physical understanding of why this should be, so this was nice, we managed to show that it's the horizon that captures the dissipation of this momentum, which I guess you would have expected. That's how things should work in ADS-CFT. But you can actually understand that physically in terms of this picture of the transverse phonon. So what's going on here is we're trying to pass some current in this direction in the boundary theory. It's going to collide in the bulk with all these atoms and set up this phonon mode. And this phonon mode propagates in the radial direction, and as it does that, it carries off some of the momentum that was in this current. But of course, when it reaches the horizon, that momentum is going to be completely lost to the system forever, and so the momentum is going to be dissipated by this extra mode. And you can see from this intuitive picture that the rate of the dissipation process, of course, happens at the horizon, which is sort of physically why it's possible to get this expression for the conductivity.
So it's the rest of the information regarding the fall of the potential in the new horizon region.
In the
You said
form
it
of the
was
graviton,
important.
you mean of the scalar field?
Of scalar field, yeah.
In the effective graviton mass
Okay,
induced.
yeah.
So the effective mass depended on the profile of the scalar field.
And there you need to have an algebraic fall off, otherwise you cannot quite identify a simple graviton mass there. Or perhaps expect it always
No.
somehow possible.
Always possible to get to this point.
Yeah.
Always possible to get to this point. Yeah. So this argument that we used about this massless mode is the reason why I didn't need to know anything about the background geometry. It's the same type of argument used in, say, establishing that eta over s is 1 over 4 pi. It's basically in any geometry the same kind of thing works. You just need to assume that there's a horizon somewhere, and that's why we didn't need to actually know what happened to our geometry. Yeah.
Confused. So whether the symmetry is explicitly broken or spontaneously broken is determine whether you have non-zero phi at the UV boundary or not. In two cases, you would have very different conductivity.
Yes, I can't answer that right now. I think it's off the top of my head.
Somehow UV has to be important.
Yes, it will come into the derivation in this derivation somewhere. Basically, this derivation does require some subtleties, and I imagine if the UV asymptotic, yes. Oh, I was confused about this yesterday. This explains it. Yes, so this formula doesn't. This formula makes some assumptions about. To derive this formula, you have to make some assumptions about the asymptotics in the UV, and I imagine this precisely enters at that point. So I imagine this formula is only true for explicitly broken. It must only be true when you have an explicit lattice. So, yeah. Yes. Good.
Assumption of the same kind should be there in the spontaneous case, but it should be richer, right? And not more things going on.
Yeah.
You still break the variable physics.
No, you will have delta function here. If it is spontaneously broken.
No.
No,
Wait, when you have an external and extra field, right?
No, if it is spontaneously broken, Hamiltonian is translationally invariant. Then you will have the.
Yeah, but then you have to pick out the conductivity associated with one of the subsystems.
I actually can see, like this, yes, this, don't worry, this won't be an issue. I can see how this works. Like there is a way to incorporate the different, this argument will rely on the fact that you've explicitly sourced the operator. So there's a point which I haven't shown you where that will enter.
Well, if you don't, if you sort of spontaneous braking, then the lattice accelerates.
Exactly, yeah, exactly.
Absolutely, right? So you want to do a holographic setup where one system forms a crystal, right, and it coexists with another system forming the metal.
Like, yeah.
Right, and that can also be put up, and you just have one system, of course.
Like that's good. That's a good point, and it will have to enter somewhere.
And so you take a piece of steel and you charge it up, you throw it out of space shuttle while you're in outer space, and that's just an ideal conductor. Yeah, that's the argument.
Right.
You can have it.
But let me present my final slide, and we can talk. Then we have as much time as we want to talk. So the final thing I want to say is how to use this formula to derive the memory matrix formula we started with that Hartnell and Hoffman used. Okay. That will be it. Good. So, if you remember from the very start, I wrote down this formula for what we expect, from a field theory point of view, the resistivity to look like, using this memory matrix approach. So, the inverse conductivity of the resistivity, Hartnell and Hoffman tell us, should scale. There was this overall quadratic term that depended on the size of the lattice. There were some factors of the momentum, And then there was this weird power law that depended on the dimension of the operator that we sourced, that we turned on. So this is part of Hoffman, and how does our memory matrix approach, how does our mass of gravity work? And you can probably see that at low temperatures in AGS2, the RH is just some constant, so everything's entering from this graviton mass. So this conductivity is just given by the effective mass at the horizon, induced by this lattice. And if you remember the formula earlier, this also had an epsilon squared KL squared at the front, but it now depended on it depended on the profile of this scalar field in the IR. So you can probably see how this is going to work now. How does this guy behave in the IR? Well, we had this nice little picture for the profile of our field. This is psi 0 of r, and this is r, and there's some horizon here. And as we mentioned earlier, this field behaves algebraically near this horizon. Okay, and that's what's going to go into this power law resistivity.
What dimension appeared in Hartnell and Hoffman's formula, or which operator was it?
The operator that broke translation invariant.
Okay, so it's not the current, for example. It's the operator that's actually. I see.
It's the scalar field.
It's the scalar field.
The scalar field, yeah.
Okay.
Yeah.
Because in the generic setting, it seems like lots of operators. Oh, I see. No, thank you.
If there were lots of operators, you'd have to include all of them and
Right,
work
right.
out them all. Yeah. Good. So I've done it with one operator.
Right.
Yeah. So this guy in the AGS2 region at low temperatures, the scalar field is just going to scale as a function of. So this is going to be my AGS2 coordinate, and it's just going to scale as some power of that coordinate set by its scaling dimension. That's the definition. So it's going to go as this coordinate zeta to the minus delta of KL. So that would be at 0 temperature, and then at finite temperature, I just need to use the fact that this is going to be capped off at some horizon radius set by the temperature. So it goes as t to the delta of KL, because the horizon radius is just 1 over t. So this tells me the size of the scalar, which precisely reproduces the Hartnell-Hoffman formula for our case. So that's basically the idea. We've done whenever you have a lattice, it's going to induce a mass for the graviton because of this phonon mode that exists. But in general, there might be lots of other things going on. So what we did was we took a very simple case where that was actually the only physics we needed to consider at this order in perturbation theory. And then we could use the mass of gravity techniques because this is the same as mass of gravity, at least on the level of the perturbation equations, to calculate the conductivity. And that conductivity is just basically the effect of graviton mass at the horizon, which is quite a nice physical way, I think, of thinking about it. Okay, I'll stop.
Any more questions?
Mike, you say that this matrix has got a massless mode.
Yeah.
So suppose you take epsilon to 0, and suppose you take the size of the lattice to 0.
Yeah.
Does this massless mode turn into delta AX, or does it turn into pi?
We get, I guess, pi. Actually, I'm not sure about that.
If it's pi, then...
It's not delta AX.
But if it turns into pi, then how can you identify this as the thing that controls the conductivity?
Because of the asymptotics. So you're looking in the region to find the conductivity at r equals 0. Actually, I don't want... Yes, so you're looking in the region r equals 0 to calculate the conductivity. So even if you turn on even if it only has an order epsilon overlap with the conductivity, it might be the thing that dominates at r equals 0. But I mean, I'd have to check the calculation, but it's not that crucial.
The ADS2 region, the scalar field would have had also the other behavior, which is d minus delta.
Yes, yeah.
Is it clear why you got this one? What selected that one out of the two?
Well, I mean, if you're at t, normalizability would fix it, right? At non-zero. It's got to be normalizable in the ADS2, right? It's not going.
It doesn't.
It doesn't.
Because the ADS2 is cut off. It doesn't.
Okay, so then there must be some slight subtlety in explaining why that one dominates.
I mean, in the sense that the whole profile, the way you got the whole profile, it should.
Sorry?
The whole profile should have fixed this. You kind of picked the source term in the UV integrating and.
Yeah, I agree.
But this is the one. This is which one did you get? You got the you got the thing which grows which.
Well, you see,
This is the. What were the two options?
so either the lattice can
1 minus delta.
it can either be
I know, but there's one that naturally dominates in the IR. And that's the one I was expecting. That's not the one he has.
Yeah.
no, because if you had that one, then the field would be getting bigger and bigger in the IR,
Oh, I see.
which isn't what physically should happen, right?
Well, H2, everything is normalizable. They all die off.
They all die off. Okay.
Let's thank Michael again.
Was-